Hello, this is Ralph Alvarado and welcome to Exploratory Text Analytics. In this video we're going to drill down more specifically on the naive Bayes classifier. Recall from the previous video that we defined the problem, the task of text classification or document classification as a Bayesian problem. So let's drill down on that. Naive Bayes is called is a particular kind of classifier that's considered to be generative. In contrast to, say, a discriminant classifier like logistic regression. Discriminant classifiers are more accurate and thus more common, but generative ones still have a role. The way this works is it assigns a float between 0 and 1 for the classification. It's not going to come out one way, specifically one way or the other. It's just going to give you a higher or lower probability for whether the document belongs to a particular category. It's performant in the sense that it may not be always the best performer, but it will always perform well, the naive Bayes classifier. It's very fast, and here's the thing, it's very easy to implement, and so it's often used as a baseline. It's a baseline against which to compare other methods. As we're going to see in one of our examples in using naive Bayes to classify literature, it actually performs better than the support vector machine, for example, in some tasks. And why is it called naive? Because it uses the independence assumption more, we'll talk about that more below, which is known to be wrong but still works. In other words, when you're talking about the relationship between words in modeling and a sentence, it just naively assumes that the words are independent of each other. And this is actually something that's been true throughout this course. Whenever we apply the Markov assumption, that's kind of naive as well. The independence assumption is always a first pass way of doing things, and you add dependency kind of as you need it in a lot of these methods. So here's Bayes' theorem. I know you all know this already, but just to make sure we're on the same page. The probability of A and B equals the probability of A times the probability of B given A. So the joint distribution of any two variables equals the joint distribution of one of the variables times the the other variable given the first variable. And here I'm saying also that the probability of B and A, and usually those are synonymous, I mean, those are considered equivalent, but I'm just going to put it this way to show you the contrary way of representing the exact same equation, which is the foundation of Bayes' rule. So Bayes' rule is saying probability of A and B equals the probability of B and A. We know this to be true since the order doesn't matter in a joint distribution. But what's on the right side of the equation, whether you begin with probability of A or you begin with probability of B, is interesting and different. And so if we make those equal, we quickly come up with this interesting formulation, which is that the probability of A given B equals the probability of A times the probability of B given A over probability of B. That is Bayes' theorem right there. So you move from this insight about how the order doesn't matter in a joint distribution probability to taking advantage of that and coming up with this equation. I think it's helpful to understand that there is a semantics to Bayes' theorem. This is something you've all learned elsewhere, but I'm just restating it just to drill down on this relationship, this what I call the arrow of information. A and B are really quite different in this equation, and it helps to keep that in mind when we're applying it to text. So in this formulation, A typically stands for the cause or the hypothesis, or from a statistical approach, the model that you're trying to predict to see which is applicable, whereas B stands for your effect or the evidence or your data. So it's basically A is to B as model is to data. Sometimes it's more ambitiously as causes to effect, but more realistically in terms of how we look at these things from the perspective of data science, we're talking about the relationship between model and data. That's always this relationship, this sort of primary ontological distinction within data science. The common words for these distributions or these probabilities are the following. The probability of A, which is, say, the probability of your cause, is called the prior. And the probability of B given A is called the likelihood. Now this is interesting because the likelihoods, it looks like a probability, but it's really not, because what you're saying is that you're saying what is the probability of the evidence that I know I have given if we assume that a model is true. So the thing is, you don't know which model is true, But in a likelihood, you say, well, let's assume one is true. If one is true, then what does the data look like? What is the probability of the data? You see, that flips things around based on what you actually have. What you actually have is your data, which by virtue of existing is certain, and what's uncertain is your model. But a likelihood is the inversion of that. And the thing about likelihoods is that we often know them from research and our domain knowledge in other areas. And I'll have a quote from a computer scientist / philosopher named Judea Pearl about that in a second. The probability of A given B is called the posterior, which is what we're looking for. It comes from the Latin terms a posteriori as opposed to a priori. And we're looking for, that which is true sort of after the fact. It's sort of like the causal output. And P of B is sometimes called a normalizing constant. It's a probability of the data, which is often really hard to find out. Sometimes it's represented by a complex integral, which is intractable. But luckily, a lot of times you can cancel out the P of B, or you can set it to 1. There are different techniques of working with it. So as a philosophical aside, just to reinforce this idea, there's a directionality implied by Bayes' theorem. A causes B. So A influences B is the assumption. Which and also it's important to remember that B must be a member of a disjoint and exhaustive set of possible outcomes from B. So lowercase b is a member of the set B, but it must be a member of a disjoint set that covers all the possibilities. So the probability of that set must sum to 1. So what we're saying is that any cause that we posit, any model that we posit, has to produce a set of outcomes which sum to 1. And I'll give you an example of that in a second. But note that P of A does not sum to 1 because each is drawn from a different or distinct distribution. And let me explain what I mean by that. So I have a diagram here. I drew this. On the left, we have things that stand for an hypothesis. And on the right, we see things that stand for evidence. And so let's just say we have a patient with red spots, and we're not sure whether the person has the measles or not. So one of our models, H, is having the measles. And measles, we're going to say, has 2 possible outcomes. It can either produce red spots, or it may not produce red spots. And we're saying here that there's an 80% chance that measles produces red spots and a 20% chance that it doesn't. And that must sum to 1. There's also the case that you don't have measles. And we, through other research, we've learned that, people can have red spots when they don't have the measles. And, that happens 30% of the time overall. That's kind of an exaggerated number. But let's just imagine that when you don't have measles, 30% of the time you can get red spots. You can get red spots from, razor burn, or you can get red spots from all these different things that are not measles. But the point is that the set of things called not measles we're treating as a kind of hypothesis, and as such it has to have a set of outcomes that sum to 1. But notice on the other side, when we're looking at the effect, and that's where our data comes from, we only have what we know is on the E side. Notice how the 2 arrows pointing to red spots do not sum to 1. It's 0.8 plus 0.3. The 2 arrows that point to no red spots, it's 0.2 and 0.7. So that's why it's important to understand that likelihoods don't sum up to 1, but the models do. The hypotheses. So it's important to keep that in mind. And I call this directionality here that's implicit in Bayes' rule, because Bayes' theorem is really an attempt to make sense of causality. I call this the arrow, or the flow of information, the arrow of information. So here's a point from the philosopher, computer scientist Judea Pearl, actually very influential, a thinker, very controversial in some ways as well. But he has a very interesting point here that I'd just like to read to you. Strictly speaking, the likelihood ratio, the likelihood of E given H, this is what we're going to call the the likelihood in the Bayes formula might depend on the content or the tacit knowledge of base K. We don't have to worry about that. That's the context. However, the power of Bayesian techniques comes primarily from the fact that in causal reasoning, this relationship, the probability of E given H, is fairly local. Namely, given that H is true, the probability of E can be estimated naturally and is not dependent on many other propositions in the knowledge base. So this is why this is what's so useful about these likelihoods, is that they're almost like components of knowledge that you can plug into your equation. For example, once we establish that a patient suffers from a given disease, H, it is natural to estimate the probability that he will develop a certain symptom, E. So if you posit, or establish that H exists, then you know what causes exist independent of other things. Regardless of what else is going on in the patient's life, for example, we know that they have this disease, then we know a distribution of what outcomes there are, what symptoms there are. So the organization of medical knowledge rests on the paradigm that a symptom is a stable characteristic of the disease and should therefore be fairly independent of other factors, such as epidemic conditions, previous diseases, and faulty diagnostic equipment. So for this reason, the conditional probabilities, probability of E given H, as opposed to probability of H given E, are the atomic relationships in Bayesian analysis. This is really important. These are your sort of units of knowledge, if you will. And this ties back to when we were doing topic models, for example, and we talked about each topic as a language model. Each topic, in a sense, is a component like this. It's saying that, what's the probability of a word given a topic? That's what one of those topics in the topic model is basically asserting. It's saying, given, if you know that this topic applies to this document, here's the distribution of words that you can expect. And so they each one of them is an hypothesis, if you will, and an atomic relationship that you can then use to talk about your collection. So anyway, that is just a side note, and I think it's really important to understand that that's what's going on when you're talking about Bayes' rule or Bayes' theorem. Here's Bayes' rules, as far as I understand it. It's not the same as Bayes' theorem. What Bayes' rule refers to is that when you are comparing hypotheses, you don't need to worry about the denominators, and you can just worry about the odds ratio of two hypotheses. So the probability of hypothesis 1 given E over the hypothesis of hypothesis over the probability of hypothesis 2 given E equals these values on the right. But notice that we don't have to worry about the probability of E because it drops out, since both equations have it, and we're just looking at the ratio of the equations, so it drops out. And that's a nice, convenient fact that allows us to more quickly, easily compute Bayes' rule. So when we apply it to text, basically we're trying to predict the class of a text, as we saw, and this becomes an argmax problem, where we're saying, what's the category of a text? Well, it's going to be for every possible category. C, C is an element of the large C. What that means is we're going to go through every single category, and we're going to plug its probabilities into this equation on the right, and we're going to get the maximum one for the document. So the document remains constant, but the class is changing. So that's what argmax, why argmax is possible to be called here. And you can see that, by Bayes' theorem, we can drop out the probability of D because it's common to all the models applied. And so all we're looking for is the probability of the likelihood times the prior. And whatever likelihood times prior produces the maximum value, that's going to be the category for the document. And remember, a document is just a joint distribution of words. We've seen that before. And F is a word in this case. That's a feature. And then, we know by the product rule that we can represent things this way. But since we are not going to be able to calculate, this equation at the top, that just gets too complicated, just like with the Markovian assumption earlier, the naive assumption here is that we don't need to worry about all these dependencies. All we're worried about is the probability of the word and the category in each case. So that's the naive assumption, is that we drop out these the results of the product rule, and we end up with this, this simpler equation to compute based on this independence assumption. Once we look at it that way, then the probability of a document giving a category is just the product of all of these likelihoods, which is really nice. And then we end up with the argmax as our value. So when we apply this to our corpus, we're talking about tokens. All right, this is pretty obvious here. And so we're talking about applying Bayes rules, the probability of the category in general times the product of the likelihoods, and then we end up with this way of computing it as logs, a sum of logs, because when we actually get to the computation of the likelihoods, we may end up with just a zero value, since these are very small numbers, and when you multiply lots of small numbers, you get what's called underflow, and you may end up with zero. So instead, we prefer to do these things using the logs. So that's the basic mathematical foundation of the naive Bayes approach. So when we train the classifier, where do we get these values? Where do we get P of C? Where do we get P of F given C? Well, we just use what's called our maximum likelihood approach. We're just basically taking frequencies of these things from a training corpus and converting them into proxies for our model. That's what the hat means. And then we're going to use those as the values that we plug into our classifier, and then we start predicting on that basis. And if we get good results, we're happy. If we don't get good results, we have to maybe use more data, mess with some parameters. But basically, this is what we're doing here. We've done this before in other contexts in this course. You have the same problems here that we have with some of the others, where if there are words in one class but not in the other, and that's very likely that you're going to have that. If you subdivide your corpus, there are going to be some words that are not going to exist in each of the training sets for each category, and so you have to do some kind of smoothing. Laplace add one smoothing and so forth. We've looked at this. This is something we can implement very easily when we do this in the notebook, but this is to be expected. There's also unknown words not in the training set at all. When we apply our model to data in the wild, if you will, and one solution is just to ignore those, or maybe assign them to a very low probability when you see them. So it works. It turns out that just regarding stop words, it doesn't help to remove them when applying the naive Bayes approach. It doesn't improve performance at all, so it's fine to leave them in. It's typical to leave them in. You might want to drop them out to improve compute speed, but it might actually help in some ways, given the fact that stop words are oftentimes elements of stylistic differences between authors. So if you are actually building a classifier, naive Bayes classifier, to do something like detect the author of a text, you might want to keep them in for that reason. Says here, not sure about keeping only TF-IDF significant words. That is, your instinct is to say, oh, let's only work with the subset of TF-IDF words. You might get better performance if you use all words. And we're not just talking about stop words. That's a case where your mileage varies. And so you may, there's a trade-off here. The more words you include in your model, the slower it's going to be. But again, naive Bayes is pretty performant to begin with. So the point here is that you don't need to spend a whole lot of time on the pre-processing part to get this going.